Hi there, and thanks for watching. This is Lab 4, Faraday's Law. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnet-tube interaction computationally, and to compare the computational predictions with the observed data from the falling magnet. The most important concept to this lab is Faraday's Law, which states that in a closed loop, the induced EMF is equal to the time derivative of the magnetic flux through that loop. So here's a brief preview of the results. Experimentally, it took 1.2 seconds for the magnet to go through the aluminum foil tube. Computationally, it took 0.25 seconds, and the computational velocity as a function of time is plotted in the graph at the bottom. In this experiment, a magnet is dropped through a tube of aluminum foil, and the time is recorded for the magnet to fall through the tube. The system is the magnet, and the surroundings is the tube of aluminum foil. The tube of aluminum foil is modeled as a series of horizontally stacked rings. For each ring, the equations to the right give us the magnetic field at that ring and the time derivative of the magnetic flux through that ring due to the falling magnet. This in turn allows us to calculate the induced current through that ring, and from that we can calculate the force of that ring on the falling magnet. So a few initial conditions for the experiment. The magnet is held above the tube and dropped from rest. The tube is held horizontally, straight up and down, and the camera begins recording before the magnet is dropped. The procedure for this experiment is pretty straightforward. Take a magnet, drop it through a tube of aluminum foil, record a video, and determine how long it took for the magnet to fall through the tube. So here are the results. On average, between the trials, it took 1.2 seconds for the magnet to fall through the tube. This is a setup for the code portion of the lab. We input the geometry of the aluminum foil tube and set the numerical parameters for the simulation. We also have an array of rings that are used to model the tube. The magnetic moment is set to the value that was calculated from lab 2, and initially we set the velocity to 0 and the time to 0. Here are the biggest parts of the code. On the upper left, we have a function to calculate the time derivative of the magnetic flux through a ring. On the right is a loop iteration to calculate and sum up the force that each ring exerts on the falling magnet. And on the bottom left, the net force on the magnet is calculated, and the velocity and position of the magnet are updated. And here's the output of the code. On the top, we have a graph of the velocity of the falling magnet with respect to time. And on the bottom, we have the amount of time that it took for the magnet to fall through the tube. So here's a brief comparison of the experimental results versus the computational results. In the experiment, it took about 1.2 seconds for the magnet to fall through the tube. And in the computational model, it took 0.25 seconds for the magnet to fall through the tube, much shorter. After some debugging, we found that in the computational model, the magnetic force of the tube on the magnet was non-zero, but basically negligible. This explains why the computational result was much smaller than the experimental result. So in the computational model, there was likely a clerical error that led to a much lower calculation of the magnetic force on the magnet than what was expected. It's also possible that the equations that were used were just limited in their ability to approximate the actual magnetic force on the magnet. It's also worth noting that in the experiment, the magnet rotated horizontally, which is inconsistent with the equations which assume that the magnet would be horizontal along the axis of the tube. So what if the resistivity were as low as possible? Well, if the resistivity were lower, then the resistance would be lower, which means that the current would be higher. This means that under the same conditions, the magnetic force on the magnet would be higher, which means that the magnet would fall through the tube more slowly. So what if holes were cut in the tube? This would mean that where there are holes, there's not a closed loop, so those loops don't carry current and don't exert force on the magnet. This would mean that the magnet would fall faster through the tube. So in conclusion, the magnet takes 1.2 seconds to fall through the tube of aluminum foil. This is significantly more time that would take for the same magnet to fall the same distance through air. This is due to Faraday's law, which states that the falling magnet induces a current in the tube of aluminum foil, which in turn induces an opposing magnetic force on the magnet, slowing the magnet down. Thanks for watching and have a great day.